Hello, my name is Ola Wassvik. I'm the CCO and co-founder of Lightbringer, and for the past 20 years, I've been doing deep tech startups, mainly as the CTO. There's been a lot of messy technology development projects, and today we're going to talk about some of them. And with me today, I have Bengt Lindoff. Welcome, Bengt.
Yeah, thank you. My name is Bengt Lindoff, and I'm Chief System Architect for a startup, Beamwave, that's working with millimeter wave radio systems for 5G and 6G. I have a background from Ericsson and Huawei for 20 plus years, where working with everything from 2G to 5G and nowadays 6G as well. And their patent is very important. So I'm an innovator and have like 600 filed patents and more than 500 granted use patents. Much of my time is spent on innovation and inventing.
Yeah, so you're the kind of core crazy inventor or inventor that really gets stuff done.
Yeah, I mean, when it comes to inventor, it can be interesting. Many people think that inventor, that is this lonely guy in a garage doing some crazy things. But here, I mean, when we talk about in the wireless industry, then it's very much about some kind of streamlined work process to get from how can you create new ideas that can be useful for the next generation's mobile communication, and then since you in order to get to the return of investment of the research.
So you're actually a structured inventor.
Yeah, exactly. So then we have. So they have more or less built up a patent factory.
Yeah.
So and that I'm one of the part of that, and that now I am using when I'm helping smaller companies, startups, to see, okay, what kind of product do you have? What kind of patent can you actually find out? Which are important parts that might be possible to patent.
Yeah.
So that helps.
But today we're actually not going to talk that much about patents.
Exactly.
We're going to talk about the things that can go wrong when you do technology development, and specifically how the initial image of what you thought you were developing or what you thought you were doing didn't go the way that you intended.
No, exactly. And again, referring to patent, it's exactly the classical that you have some fantastic idea about your product, and then you think that, okay, that is the way it's done. So you may file a patent there, and then you go out talking to customer, and then you get the real understanding of what is the actual problem. So then, I need to change or update. So it's very close to also to the patent process. This kind of, you can call it failure, or the more I would maybe not say failure. It's more that you have lack of information about what actually.
So one of my favorite quotes is that it's not what you know is wrong that is the problem.
Exactly.
It's the thing that you're absolutely sure is right that it's still not so. That's when you kind of end up in a bad situation. So you're so sure that you're doing the right thing and you're going along in that direction, and then when you meet reality or when something happens, your whole worldview collapses.
Everything that you know you don't know, that is good.
Yeah.
The problem is the thing that you don't know that you don't know.
Yeah. But I think it's even worse actually with the things that you absolutely think you know that are wrong. Like you go in with a view that we have now figured it out, and then we have the final solution when we push the pedal to the metal and we keep going, and it just turns out that there's a cliff on the other side.
Yeah.
So that's a little bit. I thought I'd start with telling one story that this is. Also, we said we're going to talk about stuff that is like 10 years in the past, so that we don't, because companies mess up all the time, but you don't want to be public with it. But things that happened a long time ago, people can talk more openly about.
Okay.
So when we did our second product at Flatfrog, we had this first product, and we wanted to make the second one like so much better. So we took in the best optical designer we can find, and he made an optimal optical design. And then we put it together in the lab, and it just worked like magic. It was amazing. And then, like 6 months later, our sourcing department came back and say, "Sorry guys, we can't produce this." Like, what do you mean? And like, well, we could produce it, but what you've actually designed and this bill of material that you gave us, that will be, to actually assemble it, will be 3 times as expensive as buying the parts. So we have made a system that, in theory, worked extremely well, and in practice, didn't work at all.
Yeah, exactly.
So do you have any examples like
that?
Yeah,
I mean, when I started at Ericsson Research, 1998, that was the time. I mean, for you who are not so old, you don't maybe not know that, but Ericsson was number 2 or 3 when it comes to mobiles in GSM at the end of the 90s. They more or less doubled the volume every year. So what I've seen, I mean, what I saw from the research point of view was exactly this manufacturing. And that means that what we had at research, that was typically that kind of feedback we get. Very good, but you should be able to do it in 100 billion pieces. So think about how should you do that so that it will be easy to mount on the PCB and all that kind of thing. So I was not involved in that step, but I realized quite early that you can do fantastic things from the on the lab bench, and I'm coming from the research, being a PhD at the university. There you are really in the front. You do something something that is totally new, and the most important is to find new things. The next step to go from that to be a product, that is knowledge that you I mean, that is also core knowledge. There are people working 30 years with that kind of thing. One of the companies I help right now, they have also people. There I have talked to people which main competence has been exactly that. Okay, how should we do this in mass production? And
so two of the terms that I had never heard when I was at university was DFM, design for manufacturing, and tolerances. So basically, okay, you have this thing, you have it in your CAD software or your ECAD, and then you go into the real world and you can't actually manufacture those things. Or you could, if you make 100,000 pieces, 2 of them will be exactly according to spec, and the other, the other 99,000 will be out of perfect spec. So you have to have like these bell curves and stuff like that. So do you have any concrete examples of when you kind of went a little bit too far in like manufacturing and production and it actually turned out to not work at all, like a project that really failed?
I would say that maybe not when you come to production as such, but going back to again the Ericsson time and Huawei time when you worked with a standardization, then we had, so to say, a concept. At the research, you develop a concept on how should 4G, 3G, 4G work, and then we had a concept, and that was sort of say what we should try to drive in the standards. And of course, we had thought on every angle on that, and saying that this is the way to do. And then once you start to talk to other companies and also people in this kind of standardization organization, and they're in some of the different groups, and one of the groups, they are really close to manufacturing, high volume production, and then you typically get information that on the procedural level or something, that's very fine, but you have to implement it, and it should be a low-cost implementation. So at the end of the day, there might not be the one, even if you thought that was the best solution, because it was some other solution that
was good enough.
Was good enough, and they could at least claim in some way that from an implementation point of view is much better.
So cost is one of the things that I think a lot of engineers underestimate how important cost is down the line. And quite often, and I've made this mistake myself, you go in and you're already assuming that you've done all the cost downs. So like you're looking at the final target, but that final target isn't achieved until you produce the 100,000 units.
No, exactly.
And if you can't produce the first 1,000 units in a reasonable way, then you will never get to the high volume.
Exactly. I mean, I was also as a young engineer, I was out driving. I mean, doing tests when Ericsson did the smartphones or the modems, the communication module inside the. I mean, this was before the smartphone, so it was the
Yep.
standard mobile phone era. But then I was out driving to do a test just to understand how the network worked.
So you were in the car trying
Yeah,
to...
actually in the car, taking dogs, and then go back to the computer, check them, and see how the hell, what's happened, and why did you drop the call here, and just for fun. And also, of course, we help the test and verification, and sometimes there was some problem that comes back to research, since it was actually something that we thought was the solution. But then it turns out there was some, call it corner cases. I mean, what you say that...
So tell me about the corner case that didn't work at all.
No, and there I can take one classical example, and this is really, really fun. That was 3D, that was soft handover. Actually, it had something with a patent also.
Okay.
So you can go really good anecdotes. So what happened was that it was about soft handover. That's talking about in 3D, a mobile could talk to two mobiles at the same time.
Yeah.
And then you have power control, and the power control needs to be fast in CDMA system. So the trick was how to make it stable.
Yep.
What was the standardization was a bit fussy. So the first movers, they take one interpretation on how you do, and then the standardization was more clear. Then when you do what you actually have to do, the problem was that now the first networks was out there with operator had this kind of fussy interpretation with these test mobiles.
Yep.
When we come out with the first mobiles, went and one of the largest customers was Hutchinson.
Yep.
In I think it was in London. There at the CTO office, at the CTO's own office.
Yeah.
If you took the phone, that was exactly that kind of problem.
So he was in the...
So when he tried to, then he dropped the call. And that was exact that kind of problems that, of course, it was not a corner case 1 to 100,000, but it's like 1 to 100 or something. So you have to solve it. But
and this was the CTO of your customer.
Yeah, exactly. Yeah. So what happened was that then, of course, the testers go there out testing. I and my colleague, which was an automatic control expert, now professor at the LTH, Lund University in Sweden. We were out, we testing, we think about it, and then we come up with an ugly solution. I mean, okay, how should we solve it? The network is that it is, even if it's not standard compliance, we have to have a fix. So then we filed that fix, by the way, and then we sent it out, and then we checked, and then there come new releases of software, and then that, so to say...
When you say an ugly fix, what do you mean by an
ugly fix? Was really tied to that specific problem.
Okay, so you basically fixed the CTO office problem.
Yeah, exactly. I mean, that was what the software in the base station at that time.
Yeah.
So you have to have it solved.
Yeah.
And then, of course, 1 year later, there was upgrades of the softwares. And then we followed the updated standard. Since that was back to the standard, we need to clearly point exactly how you should behave here. So it was potentially more what you actually should do. So, I mean, that means in the next release of phones, then this one's not a problem.
Yeah.
The fun thing is, when it comes to patent, was that 5-6 years later, when I get a search report from another patent, also related to power control, but not this kind of thing. I got one from Qualcomm, which was the largest
competitor. Yeah.
Look, hey, this is really close to what we did. That
in the CTO office fix.
So then I asked, I called our patent attorneys. Can you say they were filed like May 6 or May 7, 2004? Can you see when we filed our? 1 day before.
1 day before.
Yeah. So I mean that is also.
So they probably also had a CTO office problem somewhere.
Yeah. So that means, I mean, lessons learned here. If you go back to innovation, most likely people are working with the same kind of thing as you at the same time. So it's important that really you have to change. You can't just say, "I don't know, that is wrong." Yeah. Even if it's wrong, it's the network is out there. You have to solve. Otherwise, nobody will buy your phone. Yeah. So I mean that's quite close in some.
So this was a software fix only, or did you have to fix the hardware as well?
In this case, it was more or less a software fix.
Okay.
So it was an easy fix.
So we had this classic. You will never need more than 64K memory. When we did our mixed signal ASIC. By the way, we were. Like, it took us 6 months to decide if we were going to do one analog circuit and one digital circuit, or do a mixed signal. And in the end, we were like, no, it's going to be better if we do the mixed signal. But then we were limited on which semiconductor node we could use. Because in the digital case, we could have just shrunk it down and added like infinite memory compared to what we're doing. So we decided, but this memory will be enough. Because we and the ASIC that we were designing was intended for laptops, and suddenly the Chinese government comes in and subsidizes laptop touch, and we have to pivot, and we started doing large displays. So now suddenly we need to crunch 10 times more data through our, and we couldn't redo the chip because it cost us $5 million to do the chip. So for like 10 years, there was one guy whose basically only job was how to optimize the memory even further. And we managed to in software, crunch out to get like 10x performance or even like 30x performance out of that tiny memory. But that was one guy's job for a very long time.
But I mean, that's quite amazing that you actually could. When you have, so to say, the knife.
The limitation was there. We had already done the chip, and the chip worked perfect. We actually got it first time right, which is like unlikely when you're a small company. Well, it's unlikely for any company. Maybe not with AI nowadays. Maybe they can do first time right all the time. But we really couldn't afford to redo it. So we just had to kind of live with how it ended up.
Exactly. Yeah. You have to do.
Do you have any similar things where you kind of like, okay, now you're constrained by the hardware because that just can't change, and you have to kind of squeeze yourself into it?
I mean, that was the closest one that I know about. But you also, going back to the innovation, I think you can do a lot. And I think this is also something that I think drive innovation. This kind of failures or what say, oh shit, that was not what I thought about. Since then you have to rethink. And again, even if you think that your idea is the best in the world, it's actually, so that was one that said to me quite clearly, and that's, I mean, of course, it's quite common. I mean, it's well known once you know it, but even if, regardless of product, nothing sells by itself.
No.
So that means that, okay, if it turns out that you are on a wrong track, you think that this is the product, and then it turns out it might be cost, it might be that the customers might not have that kind of specific issue. You have to change. Since you can't sort of tweak the entire world.
No. You can't force everyone else to do what you're doing, unless it's really, really important that you change. Then it can be an advantage to push everyone, so that everyone else
might be some odd outliers on that.
So one of the things that I've encountered many times, and at the first, like at the beginning of it, I was on the wrong side, and then afterwards we were on the right side. I was standards. So like when you're influencing a standard, you're basically helping set the standard, versus someone else set the standard based on what they built, and you just have to squeeze in. So we had this case where Qualcomm, the company that does the digital signing pens, they had basically told Microsoft how to write their spec on digital pens for laptops, and we came in. And we sent our device off to testing at Microsoft, and they just said fail, and we're like, what happened? And then we sent it again, and we had tested like in-house, and it came back and said failed, and we're like, so then we went there and we checked, and it turned out that their test finger that they used was not an actual finger; it was a piece of metal cloth, because that's what worked best for Wacom. And it's like it simulated what the finger would look like, but of course a piece of metal cloth that was complete half transparent didn't work with an optical solution. So it took us so much time to kind of convince Microsoft that this is not actually a finger. But they're like, no, this is the standard, this is what we should go with. So there we actually had to affect the standard. Have you had any similar experiences where you kind of like someone else has set the standard and it's just like, this is wrong?
Exactly. Typically when it comes to 3D people, the standard is often quite loose in the sense that you need to, I mean, that's some kind of minimum requirement. And then in some areas there will be tougher requirements due to user experience and that kind of thing. And there was one typical example on that. We had a specific receiver architecture that we have designed with a lot of patents around it, of course. And then a competitor had another receiver design, and they were a bit ahead of us. So they start to talk to the operators about what's really counts. So of course there is this kind of, this is at least you need to fulfill this kind of performance.
Yeah.
But you have to get better, especially in these important scenarios.
Yeah.
And that actually was scenarios where their receiver was optimized.
Yes, exactly.
So once we came there with that was not optimized.
No.
So then we have to say that but it's not always these. But then you are the second one, and you have to convince them. So it's very, very close to that if you are the first, you can set de facto standard.
Yeah.
As long as you can show good behavior in general, then you can find these kind of pinpoints where you may know that you are outstanding.
Yeah, we had a similar thing when we were doing a lot of tenders. Like this were government tenders, and you went in and you looked at the tender, and I can tell you this happens all the time still. You go in and look at the tender, and there is some crazy point. Like, why on earth would you need this thing to work in this system? And it's clear that it's just so that the person writing the tender want to have a specific supplier. So you kind of design in. And then when you figure that out, you can say like, oh, okay, what are my products best at that no one else can do? And then you just say, okay, why don't you look at how important this feature is? So, but you keep saying that the standards are quite loose.
Yeah, in many cases, in the sense that they are sufficient.
Yeah.
In some ways.
So you just need to reach. But what about interoperability? Is that required? You need to, like Ericsson had to work with Qualcomm
of course.
systems.
So there you have this unfairness in the sense that the base station can choose which features to support.
Yeah. Okay.
But the mobile have to support everything.
Yeah.
So that I would say that mobile, the ones that doing the modems for this, I mean, there are not so many companies that doing the entire modem.
Yeah.
It's one of the most complex system in the world, I claim.
Yeah.
There is a lot of things you have to support all.
Yeah. And RF for a long time has been like considered almost black box magic. Whenever we sent away for FCC testing or whatever, it felt like it could be quite random if you passed it or not. We had these systems where in the end, we couldn't make them pass FCC B testing, and one of the engineers said, let's just put some copper tape here in the corners and see if it works. And it works perfectly. And everyone that was probably the problem, but it didn't make sense. It was like there shouldn't have been leakage there, but it still was. So RF is very complex subject.
Yeah, exactly. Especially if in real environment, you should test in all kind of corners. And of course, you have very good models when you develop it. But when I talk to RF designers, they typically say that we think, but we have to measure when we have the actual chip before we can be really sure. So
when talking hardware, one of the things that also I learned, and another quote that I love, is that in large enough volume, anything that can go wrong will. So we had this. So one of the classic ones is when we started doing high volume PCB manufacturing, and we have picked a BGA capsule for our ASIC. At some point, you need to use dual source suppliers for multiple reasons. Their factory might burn down, or there might be other problems. And like getting a new factory up and running, typically the first 6 months, everything goes really well because their engineers are on every topic and things just keep running. And then typically in the middle of the night, you get a phone call saying, everything is not working. We're not getting anything out of the supply chain. I think it took us like 6 months to figure out what went wrong. And in the end, there was someone who had changed the cleaning liquid. It was the right cleaning liquid, but it wasn't pure enough. So when it kind of went in, it became... And it was like these intermittent failures. It was only during certain scenarios that the solder joints cracked a little bit, so that they opened up and didn't work, and then they started working again, and it was a mess. That was the first time I was like okay, when we scale enough high volume, it just strange things start happening.
Okay.
That you just like after the 6 months looking into it, it's like that was obvious, but when you're at the start and nothing works, then you're like, what is happening now, and why can't just everything go smoothly?
Referring back to I'm a PhD in mathematical statistics. That is the ergo theory. I mean that if you just search all kind of errors, you will eventually find them.
You will find all errors.
You won't find it with 1,000 or 100,000, but with 10 millions or 100 millions.
When thinking about like bug hunting, do you have any like strategy for how to approach it?
I think it's the interesting thing with bug hunting is that you don't know. I mean, this is the thing that you don't know. You don't know that you don't know.
Yeah.
So that means that what's happened is that you can't think about it before.
No, exactly.
So I used to say that now when I work with Beamwave or in general, that okay, we have tried to squeeze out and mine everything, all kind of things, but for sure, when we come, so to say, to the real production line, there will be something.
Yeah.
And then you have this kind of alarm clock, or you have to solve it. But then you will blame, why didn't I thought about that?
Yeah.
So bug hunting, then of course, what the strategy is, it heavily depends on what kind of bug it is. And then, of course, if you have experience, you have a lot of tools that you can try.
Yeah.
And again, now with generative AI, you can also use that to problem solve. Maybe there is some tools you don't aware of, but there is aware of in another field that have some kind of the same methodology.
Yeah, one of the things is so for really, really important projects, we used to do FMEAs, failure mode effect analysis. But it took such time. Basically, every engineer had to think about every possible problem that could go wrong, and we score them, and we try to at least fix the top ones or preemptively look at them. But that is something that I really see where AI can help out.
Yeah, exactly.
Basically, just okay, this is my entire product. Do a failure mode effect analysis on it and see what happens.
They can work a bit faster than you as a human can do. So
yeah. In the field we were working in, there were some safety standards.
Yeah.
So we had, for example, eye safety. You were not allowed to do certain things, and specifically we had to do double fault analysis. So basically, the system should still be safe while it was faulty. So you could have a single fault, like something goes wrong, and the system then, even though it's wrong, it cannot break the safety standard.
No, exactly.
Are there similar things in telecom, or?
Yeah, I mean, you have this kind of SAR rules for the phone, but I have working with one client now. They have exactly that kind of thing. That I mean, once you're working with like laser rather. Yeah, exactly. Then you have this. You have to solve it even if everything gets wrong.
Exactly.
Yeah? And I understand this is really tricky, and you need to have a lot of fail-safe mechanism to.
Yeah. No, and we had this where we figured out that during like 25 milliseconds, the LED could fire at such strength that it could affect an eye if you were looking at it through a microscope, through a magnifying glass. And that was part of the standard.
Okay,
People were like, I mean, so it's like someone goes up to the screen with a magnifying glass and looks like this, and right then the system fails. And you still have to be safe. It's just like, I understand why safety standards is like that, but sometimes it felt like, oh, this is a little bit pushing it. But on the other hand, the product was completely safe.
See, I will take this one. It's 6 billion out there. 6 billion people that having a smartphone.
Yeah.
And you pick it up, everyone pick it up 100 times a day.
Yeah.
It's not unlike that someone just take it.
Take a look at it. No. And again, in large enough volume, it will happen.
Exactly.
Yeah. when you're on the plane, you always see this picture. If your phone just randomly catches fire when you're sitting there, and of course, it's never happened to me. No. But in theory, it will happen at some point. Some battery will be damaged
Yeah,
so
and,
that
as far as that has actually happened.
So
Exactly.
it's for a reason that they have those.
Yeah,
but
exactly.
when you're an engineer, you're trying to look at all these different things, and sometimes you're just shaking your head like, why do we have to do this thing? But it is good that we have safety standards. Otherwise, people would be designing whatever.
Yeah, I mean, referring to this kind of safety or high throughput requirements. I mean, these were ultra low latency stuff that was quite hot like 10 years ago in the standardization. Then, of course, we worked with that. I worked with that quite early, and then you had this 9.99999s or something like that, 10 to the minus 9. But then actually you see that, of course, you can design the communication protocol of that. But once you start to lift your helicopter, you one step up, but then you need to have redundancy system, all this kind of what you have in airplanes. You can't solve it with one. Maybe the tiny communication you can do, but there is, if that you will mean that it's the entire system. And then you need to have what they have in airplanes, like 3 independent system and all that stuff. Otherwise, you can't.
That's actually how we solved one of our critical issues we had, was that like we imposed upon ourselves a too hard specification. So like in our systems, we had like 200 different channels that communicated with each other. And internally, we said it's only allowed that one channel fails over the lifetime of the product. And why did we do that? Because me and some other people sat in a room and said, okay, what is reasonable? Well, one will probably have to fail during the lifetime. And then we went into the field for different reasons. Typically, like over the lifetime of the product, 2 to 3 channels would fail. Like because typically because of transportation, like you were shipping something somewhere, and by random chance you end up in the top container on a ship, and it happens to be 60 degrees while it's stuck it's like things like that.
Exactly.
And then we got this, and then we had put in basically a system that said, okay, if more than one channel, then the system doesn't work anymore. Like we shut it down.
Okay. That was a problem.
So we got like a field return saying, the system shut down, and we're like, was it failing before? No, it seemed to work fine. And then one of the engineers said, why don't we just stop shutting down the system and see what happens? And suddenly, no complaints. Because the customer couldn't actually tell any difference, because the area affected on these displays was just so small. So this was kind of working in the other direction. 99.9% of the time, no one would ever touch that specific little part of the screen. And we could kind of relax this specification that we had put upon ourselves.
Exactly.
Because we were engineers, and
too tough.
We were too tough on ourselves. And the customer didn't care. They just wanted a system that worked well.
It should work. They don't care well.
And I think this good enough is something that a lot of engineers are like,
good enough, exactly.
They are not satisfied with good enough. It needs to be perfect. Whereas the salesperson just wants to sell something that is good enough and that can compete against the competition.
I mean, engineers are problem solvers. First, when the problem is totally solved, you can be satisfied.
Exactly. And you can put an engineer in a room, and they will just continue working and making it better and better. And that's good engineers, by the way. You don't want engineers that's like, I will just let this go.
But I get again, it's a skill to know when to stop. Since you can always improve somewhere.
I think there will be a lot of great developments using AI, like super smart engineers and researchers using AI to kind of go fast in the right direction and do evaluations that would take far too long before.
And then you're back to what's called Jevons paradox. I mean, since it's fast, you can do even more. And then the same, we can even better, even more detail. But again, if it is a product, stop where you think it is sufficient, even if you are an engineer. And then say, okay, this is sufficient. And then it's maybe better. So that's a sales guy that don't have this kind of personal feeling to the technical solution.
And that goes for, I think that almost every engineer that I've ever worked with had a sense of true pride in the work that they do that is sometimes not connected to what the customer needs.
No,
It's like, okay,
Exactly.
this is my work and this is what I do great, but there's a disconnect between the thing that the business wants to sell and what the engineers want
But
to
again,
deliver.
when it comes to startups, that could also be one reason that many startups are started out like researchers or other, and that might not be them that will be the one driving, so to say, the full scale. It might be another skills to drive it on the full scale. When you have to sell something, then it's another skill. Sometimes I guess that founders with this kind of research engineer genes is too far at this as a CEO. But maybe that's better now. But that's my feeling that it's sometimes you change. There will be another things that is important. You should be there, of course, as like maybe CTO or something like that. But for the sales, then
I think it's a truly underestimated skill for a CTO to be able to sell. Like for the CTO to be on the front line versus the customer, because otherwise there's always communication gaps. If the salesperson goes out and then he comes back and talks to the CTO, who then talks to his engineering team. You have like this is like the whisper game. Someone says something and the CTO then interprets it instead of the CTO actually being in the sales meeting. And that's where I always was, and it was great, like seeing the customer reaction to the product and kind of learning when a customer reaction was good and when it was just like meh. I very much remember two distinct cases. Like we always went to these trade shows, ISE, because we knew that all our customers would be there. So it's usually good for tech companies, for like deep tech companies, to go to the trade show where all their like you don't have to go to Japan and Korea and the US. So you can go to a single place and meet everyone. And we had this one product that had a really nice industrial design, and the team was just like, well, does this really matter? Like, is this really important? Because it would be so much easier to make it a little less nice looking. And I was like, no, this is what we're gonna do. Just let's go with this one and test it with the customer. And we had this Japanese client come in, and this was the VP R&D at that Japanese company, and he just went up in front of the product and just stood there looking at it for like 5 minutes and not even using it. And then he basically looked at me and said, so does this work? I was like, yes. And he went up and touched it and it worked, and he was like, this is magic. Because in his mind at that point, that wasn't supposed to work, because his mental model of how these systems works was different.
Yeah, okay, yeah, exactly.
And on the other hand, we then had another product where we had spent so much time. This was also connected to industrial design. I again had another hypothesis that this would really blow people away, and we had people come into the room and test it, and there was no reaction, like none at all. We had spent 2,000 hours trying to get this product. We could have made a mock-up and put it in front of the client, and they would have said, nah, I don't care. And we spent so much time actually trying to make it work so that the demo would be perfect, because I had seen this other reaction. And after that, we actually just started making mock-ups. So instead of actually making it work, we just made a mock-up, put it in our little private room, and if you got a good reaction from the customer, then we would actually try to make it work instead of spending 2,000 hours and $1 million trying to make a product that no one wanted.
No, exactly. Just to see whether they are thinking that this is what they want.
Yeah.
Referring to what you said about this kind of design, the classical thing, but again, it's 25 years or more since a mobile phone had an antenna.
Yeah.
And that is also classical, that everyone that is an engineer, it's a totally stupid thing to plug in the antenna inside. So, and I know that there was a lot of discussions in
Who did that first? Was it Nokia that did it?
Yeah, I think it was. Ericsson was late. And Ericsson was very engineer driven, also on high level.
Yeah.
So then.
Yeah. So the engineer said it has to be an antenna.
Yeah, exactly. Otherwise it will not work. Yeah, but again, we have this sufficient.
Yeah. But the thing is that the customer doesn't care. They just want magic. They don't want to understand how the system works. They just want it to work.
Exactly. And another thing that has been on the good old day when we have a read phone line, and again refer to when I studied at the university as a master student. Then you had a lot of ways to derive this 99.99 percentage of the line.
Okay.
Yeah, exactly. So I mean, you never drop the call line when you have copper. But once people start to have this one, of course they were annoying the first time that it was dropping. But on the other side, they have never ever before been able to call from a wood forest far away from everything. So what's happened nowadays? People are used to that. So what's happened? You are out driving in the car, or like you're sitting on a train up to Småland, where and you have some phone call and then suddenly it dropped. And then you said, it's I'm in the darkest part of Småland. Yeah, I know, we can wait. Yeah. So now people are used to a bad system to some extent.
Yeah, I actually have on the train line that I'm going, there's a specific spot, and it's not in the middle of the forest. There's a specific spot between Eslöv and Höv where everyone always drops a call with my wireless. So
I mean, that is one thing that is sufficient. Since people can stand out with that, since you have so much other benefits.
Yeah.
So
and nowadays I typically don't call people until after I pass that point.
Exactly.
Because I know it's going to happen, so it's just annoying.
Yeah, exactly.
I hope you enjoy these conversations about how things can go wrong when you do technical development. So once again, I'm Ola Wassvik, and with me
I have Bengt Lindoff.
So thank you for today.